This math talk will be my last application of quadratic optimization, and it's a pretty common one. I've got a rock being tossed upward from a tall cliff, and the height h of the rock above the base of the cliff in meters at t seconds after being tossed is given by the equation h equals negative 4.9 t squared plus 18t plus 68. Now, I deliberately gave you where the factoring and some of the algebra just doesn't look all that nice. And you're going to realize that it's really no more difficult than anything that we've done. What I'm asking you is to determine the maximum height reached by the rock and the time that this occurs, and round all your answers to one decimal place. We recognize that although the numbers are not that convenient to work with, it's not going to be a problem because we can grab for a calculator in this situation. Graphically, we're looking at a situation like this where we have height versus time, and it's a parabola. You'll notice that I've cut off part of my curve simply because our rock is tossed in the air at time equals 0, and prior to that it isn't actually a projectile moving, so I'm cutting off my curve at one point. Now, once again, I'm going to use symmetric points as I did in the Golden Gate Bridge example, and the algebra goes something like this. I common factor out my negative 4.9t out of the negative 4.9t squared plus 18t. What I have left behind inside the brackets is 18 divided by 4.9. And I'm not too worried about that because I can grab from my calculator when I need to get that value. And so what I recognize in this is that when t is equal to 0, h becomes 68 because much of the right-hand side disappears. And so I have the point 0 and 68. Now when I let t equal, and I make it that 18 over 4.9, or approximately 3.673, h is approximately 68 again. And so I plot that other symmetric point. Now in the question I did ask you to round answers to one decimal place. You always round your final answers to one decimal place. Carry a minimum of one extra decimal place, if not two, in all of your intermediate calculations and round in the final step. So that's why I've reported 3.673. Now, in order to find the vertex, we recognize that the vertex lies directly on that axis of symmetry. So in other words, the t-value of the vertex is halfway between the two t-intercepts of our graph. And so we say the t-value is 0 plus 3.673 divided by 2. And so we get a t-value of 1.837. The h value, substituting in the 1.837 back in the original equation, and we get 84.5. At that point, I'm going to round my answers and say the maximum height reached by the rock is approximately 84.5 meters, and it is reached approximately 1.8 seconds after being tossed. Really, the problem was no more difficult using the awkward numbers. Thanks for watching.